All right, this is Math 331, Lecture 4. Does that sound right? Yeah, Lecture 4. So what I want to do today is I want to talk a little bit about recurrence relations, and I want to talk a little bit about the arithmetic mean, geometric mean. Out of curiosity, how many of you have done recurrence relations, solving recurrence relations? How many of you have done generating functions? How many of you are comfortable with generating functions? Okay. Now I feel a little bit better about doing this. So, even better.
Yeah.
So, this is a class which is in some sense wild card. Did you get a solution key? Right. So 1-for-1 trade. So, this is a class where you are going to occasionally be seeing things you've seen before, but the hope is that you'll see them in a different light, and we'll do it in a more unified way. For the most part, I'm going to concentrate today on recurrence relations with just one index. That's typically what people do, and then you can look at recurrence relations with 2 indices or 3 indices or 4 indices. One of the examples you might have seen is Pascal's triangle. And maybe T and K is the kth element in the nth row. And that's just our n choose k. And then we have a wonderful rule, n plus 1 choose k plus 1 is n choose k plus n choose k plus 1. And so we can write this as t n plus 1 k plus 1 is t n k plus t n k plus 1. So this would be a recurrence relation where now you have 2 indices. And the question is, can you somehow go from this and solve and get that t n k is n choose k, at least if I give you the initial conditions? Has everybody seen Pascal's triangle? The 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. You might have seen proofs of this using like the binomial theorem, expanding things out. This is what you get when you expand x plus y to the n. This will be the sum. K goes from 0 to n choose k, x to the k, y to the n minus k. And this is the binomial theorem. And one way to interpret this is when I expand this out, every term is going to just be some number of x's and y's. The sum of the powers of x and y must add up to n. If I have k x's, then I have to have n minus k y's. And so how many ways, when I have n factors, can I choose k of the factors to give an x? It's n choose k. So this is the combinatorial interpretation of what's going on. This is one of the most important identities in mathematics. So many things come down to the binomial theorem. If you want, I'll give you another proof of Pascal's triangle of this formula through story. Have you seen the story proof of this? All right, let's do the story proof. I need an outstanding, awesome college. This is being recorded, guys.
I was going to say it.
Wow. That was a long delay. All right, well, I think the reason I'm trying to save your asses now because this is going to be on the web. I think the reason you paused is that there are so many awesome colleges in the world that it was tough for you to choose just one. So I'll make the next question easier. Give me the worst possible college you could think of.
Amherst.
Yeah, that was much faster.
Yeah.
All right. So I'm going to choose a group that will have n people from Williams and 1 person from Amherst. And I want to form from this a group of k plus 1 people. So I want to choose k plus 1 people. So how many ways are there to choose k plus 1 people from n plus 1 people?
N plus 1 choose k plus 1.
N plus 1 choose k plus 1. And now, so much of combinatorics is counting things 2 different ways. I'm going to break it up on whether or not I have the Amherst person. So I either choose them or I don't choose them. If I choose them, how many ways is there to choose the Amherst person? 1 choose 1. I have to choose that person. Now I have n people left from Williams. How many ways can I choose k people? And choose k. Or I don't choose the Amherst person. One choose 0 way of not doing that. And now how many people do I choose from Williams? K plus 1. So this is a story proof. Did I make a mistake?
Just n on the top right, on the far right term.
Oh yes, just n, thank you, yes, just n. Yes. And now what you notice is this is just equal to 1, and this is just equal to number 1. So you often don't bother writing them down in your formulas. But if you think about what's going on, what's nice about this is the top sum to n plus 1, the bottom sum to k plus 1. I have n plus 1 people that I'm working with, the tops are always summing to that. And this is proof by story. It's one of the best ways of proving something. We'll do a lot more with proof by stories later, but given that we were talking about the binomial theorem and recurrence relations, this is a nice way to put it up there. And it's a nice way to emphasize the fact that there are frequently more than one way to prove something. Different proofs will highlight different things. All right. How many of you are familiar with Binet's formula about the Fibonacci numbers, the formula for the nth term of the Fibonacci's? Okay. This is one of my favorite formulas in all of mathematics. It is phenomenal. It allows you to jump to whatever term you want. So I'm going to show you generating functions for the Fibonacci's. Later we will almost surely look at generating functions for more interesting involved things. So for the Fibonacci's, we have f0 is 0, f1 is 1, and fn plus 1 is fn plus fn minus 1. If your entire grade for the semester, hell, let's make it your entire college career, depends on calculating the 2000th term of the Fibonacci's by hand, no computers, you up for it?
Do we have like 4 years to do it?
Yeah, 4 years. You have 4 years to do it. 4 years.
Then I'm okay with that.
Yeah.
Yes. This is not a hard problem. If you had a computer that could only add, still not a hard problem. You don't need that much to do this. But it can become very time consuming. And so if you look at some of the Project Euler stuff, if you want to look at the 2000th or the 20,000th Fibonacci number, it would take a while. There's a way to jump to any term in the sequence. There's an explicit formula. It's one of my favorite formulas. And so here's how it starts. We're going to use what's called generating functions. And I'm going to define g of x to be the sum, n goes from 0 to infinity, of fn x to the n. So I'm taking the information about the Fibonacci's and I'm embedding that into a function. Now at first you might go, how can this help us? Because the whole point is we're trying to understand the Fibonacci numbers. If we can get a closed form expression for g, maybe we could then use a closed form expression for g to then deduce things about the fn's. You have to remember, once I write this stuff down here, the Fibonacci numbers are completely determined. There is no mystery anymore in the Fibonacci numbers. It's just a result of doing a computation. How many of you have taken differential equations? Have you done series expansions?
I don't remember.
Okay. One of my professors used to say, recall if you do not already know. So if you look at series expansions to try to solve differential equations, it's very similar to what we're going to do here. So let's look at g of x. This is the same as the sum. I'm going to shift things around a little bit. I'll write it as m goes from 0 to infinity of f, let's do maybe like f n plus 1 x to the m plus 1. Well, let's, I want to stop. Just think where I want to stop. Yes, I'll start here. So if you look at this now, I'm just replacing n with m plus 1. Now my first term is going to be f2. So I don't have the f1x term. So I have to add the f1x term. Do I have to add the f0x to the 0 term? No, because f0 is just 0. The reason I'm writing it like this is I know a formula for fn plus 1. So since I have fn plus 1, I can now use the Fibonacci relation here. And the goal is to get your expression that you want twice. So I'm using the letter m. Some people would often use the letter n. and they would do the change of variables, let n equal n plus 1. I know people sometimes find this confusing because how can n be n plus 1? You're replacing n with n plus 1. So sometimes people do it in 2 steps. Let's use the letter m, and I'll have n equal n plus 1, and now we'll replace m with n. All right. So continuing, we get this is the sum, n goes from 1 to infinity, of fm plus fm minus 1, x to the m plus 1 plus x, because we know f1 is just 1. All right, so this is the sum, m goes from 1 to infinity, of fm x to the m plus 1, plus the sum, m goes from 1 to infinity, of fm minus 1 x to the m plus 1 plus x. So when you look at this, a huge amount of math is algebra. It's how do you do the algebra to see something nice. What would you like to do to this expression, fm x to the m plus 1?
Make it fm x to the n.
Yeah, we have g of x is the sum of fn x to the n, where this index is the same as that index. So we'd want to pull out an x. So this would be the same as x, the sum, m goes from 1 to infinity, of fm xm. For this one, what would we want to pull out?
X squared.
An x squared. Then we have a sum, m goes from 1 to infinity, of fm minus 1, xm minus 1, plus x. And now if you look and see what we have here, this function is almost the same as g of x. It differs from g of x in that it doesn't have the f0 term. Oh, but what's the f0 term? 0. So this is just going to be x g of x. All right, the next piece, well, when m starts at 1, we get, oh, we have f, beautiful, we have it perfectly, plus x squared g of x plus x. All right, so I can write that up here as x g of x plus x squared g of x plus x. All right, so any questions on what we've done up till now? Everything good?
I feel like I'm good mathematically speaking, but I just still don't understand how this would be like faster. That makes sense.
Well, right now it's not clear.
Oh, okay.
The miracle hasn't happened. This is going to give us an explicit formula for fn, and then we'll get it for all of it. Right now, the idea is we're using local information to create a global object. So if you've seen anything with elliptic curves, if you've seen anything with the Riemann zeta function, this is something we do all the time. We take local bits that we know and we use it to form a function. And then somehow from that function, we can sometimes deduce things backwards. So we have this global object. It would be wonderful if we knew what g of x is. We don't, but we have this interesting relationship for g of x. We have g of x is equal to x g of x plus x squared g of x plus x. So we should solve for g of x. So we get 1 minus x squared times g of x equals x. So we get g of x is x over 1 minus x squared. Or if you want, a very bad way to write it is like this. So this is an absolutely horrible idea. It seems natural because this is now set up so I can use the geometric series. We know that 1 over 1 minus r is 1 plus r squared plus r cubed. So just take r to be x plus x squared. So we could use the geometric series formula to expand this out. The problem with that is r is not homogeneous in x. It has a term of size x and a term of size x squared. So when you expand things out, it would be a nightmare. You would then get g of x is x times 1 plus x squared plus x squared squared plus x squared cubed. So this piece will give you terms of size x and x squared. This piece will give you terms of size x squared, x cubed, and x to the 4th. This will give you terms of size x cubed. all the way up to x to the 6th. So if I wanted to find the x to the 5th term, I would have lots of different factors contributing to it. And that's why this is not a good idea, because these are mixed degrees. So this is not worth doing, so we're going to destroy this. All right. Is there another way we could try to use it? We love the geometric series formula. I'd love to use the geometric series formula, but the fact that these have different degrees. Anybody have any idea of what we could do? It is a calculus technique, which is the least favored or most hated of all the calculus techniques. The only time people don't list it as their least favorite is when they've been so traumatized by it that they forget they've learned it.
Partial fractions.
Yes!
Wow.
Partial fractions. You write this as x times a over 1 minus alpha x plus b over 1 minus beta x. I can just pull out the x, and now I expand the denominator. I factor the denominator. And now what's nice is I can then expand these using the geometric series formula. And now everything is of the same degree. And then I would get g of x is going to be x times the sum, and goes from 0 to infinity, of a alpha to the n plus b beta to the n x to the n. So I'm not going to go through the details now. I will leave that to you as to how do you do the partial fractions, how do you find a, b, alpha, and beta. It's a good exercise for you to go through and do this. When the dust settles, you get fn is 1 over square root of 5, 1 plus root 5 over 2 to the n, minus 1 over square root of 5, 1 minus root 5 over 2 to the n. And this is often called Benet's formula. And what I love about this is, imagine you are walking on a street and a number comes and beats you up. Okay? So the police are investigating and trying to, and they're going to do a police lineup. And they gather a bunch of numbers and they put the number. And it was dark, you don't really remember all the details, but you remember it was an integer that did it to you. Does this look like an integer? You've got square roots of 5, you've got divisions of 2. This will always end up to be an integer. A nice question is, what can you change the 5 into the 2 by and still have it always be an integer? There's a lot of other nice things about this. So one thing is, I can just jump to the nth Fibonacci number. Wonderful. Now, this number over here, 1 plus root 5 over 2, this is the golden mean. It's greater than 1 in absolute value. So this term is exponentially growing. 1 minus root 5 over 2. In absolute value, this is less than 1. This term is exponentially decaying. If n is large, this term is essentially 0. So when you're trying to calculate the Fibonacci numbers, you know the Fibonacci numbers are integers. You just have to calculate what's the closest integer to this. And that'll be your Fibonacci number. So you actually don't even need to worry about this part over here because you know it's an integer. And you only have to calculate things well enough to figure out what the integer part of this is. The non-integer part will be perfectly balanced with that. So this is one of many ways to get to Benet's formula. And what's truly wonderful about this is, from a computational point of view, you can jump to whatever you want. And then there are tricks. If you want to raise something to the nth power, there are fast ways to calculate something to the nth power. So you can make it even faster than just this. But this is the power of generating functions. You start off with an expression, with local information, and if you are lucky enough to get a global object, you can then often deduce things backwards. This might remind you of a calculus technique, the bring it over method, where sometimes when you're trying to do integrals, you get, after you integrate by parts twice, you get what you started with on both sides of the equation, but with a different weight in front of it. I think probably one of the standard examples might be maybe like integrating maybe sine of x times e to the x dx. Something like this. Because when you integrate by parts twice, sine will go to cosine, will go to sine. It's probably a negative sign somewhere. and you'll get things to work out. So problems like this you can solve by this, bring it over, and you'll get the expression you want on both sides of the equation. That's exactly what we did with the g of x. We got g of x on both sides of the equation, and since it was on both sides of the equation, we could then solve for it. As long as this coefficient here isn't 1, we win. All right. So this is the idea of generating functions. This shows you how you can use generating functions to solve recurrences such as the Fibonacci's. There's a lot you can do with recurrence relations, and a huge number of problems and competitions come down to coming up with a recurrence and solving it. So I want to talk a little bit about how to solve recurrence relations. So there's a lot of different proof techniques. How many of you have heard of the method of divine inspiration? How does the method of divine inspiration work?
You just stand there until God gives you the answer?
Basically, yes. That is the method of divine inspiration. What is the problem with this method?
God is fickle.
Wow.
I don't know if I'll say God is fickle, but God may not deem you worthy. So, but for a lot of problems, if you write down the answer and just check and see if it works, that's fine. It doesn't matter. So one way to prove the quadratic formula is to just write down, let's look at x minus root 1 times x minus root 2 and expand it out and say, look, oh, we get ax squared plus bx plus c. We solved it. Or if I want to factor a large number, if I just write down the factors and multiply them and it works, I factored it correctly. There's a lot of problems where you can just check and see if the answer is right. So I'm going to show you how to solve recurrence relations using the method of divine inspiration. So let's say we have an plus 1 is 3an minus 2an minus 1. Okay. So let's guess that an equals r to the n. Let's just guess that our solution has a form like this. And we talked last time for the Fibonacci numbers why this was reasonable. We showed how the Fibonacci numbers grow slower than 2 to the n and faster than root 2 to the n. So it made sense to guess that maybe the Fibonacci's are growing at an exponential rate. Let's try something like that here. If we plug this in, we get r to the n plus 1 is 3r to the n minus 2r to the n minus 1. Bring things over, I get r to the n plus 1 minus 3r to the n plus 2r to the n minus 1 equals 0. So I pull out an r to the n, and I'll get r squared minus 3r plus 2 equals 0. So, did I make a mistake? It should be, yes, it should be r to the n minus 1. Thank you. So this basically gives me r equals 0. Well, that's not really interesting, because if I take all the an's to be zeros, yes, that will solve the recurrence relation. I'm looking for a more interesting solution. Now I want to solve this equals 0, and so you factor this. So this you can write as r minus 2, r minus 1 equals 0. So we get r equals 2 and r equals 1. And so we've just found two solutions to this. I can take 2 to the n, or I could just take 1 to the n. And if I take, an to be 1, for all values of n, it's going to work. In general, I don't have to look at a recurrence relation of length 2. I could look at like 3, 4, 5, etc. As long as the length is fixed, I can do this. And then I would just get more roots. And then this is where it's nice that the coefficients here do not depend on n. This is a linear recurrence of fixed length. So it's linear, and it's fixed depth. So if r to the n is a solution, and u to the n is a solution, so is their linear combination. So has everybody here taken linear algebra? Basically, we're looking at the span. So if I have two solutions, they're linear combinations. So the most general solution is going to be the form C1 R1 to the n plus C2 R2 to the n. And now I figure out what C1 and C2 are based on initial conditions. And so if I know A1 equals 1 and A2 equals 4, I could then say, oh, okay, I would get, so in my case, I've got R1 is 2, and very nicely, R2 is just 1, so 1 to the n is just 1. So I would get 1 equals 2C1 plus C2. 4 is equal to 4C1 plus C2. Or writing in a matrix form, 1, 4 is 2, 1, 4, 1, C1, C2. And now I can use linear algebra to solve for C1 and C2. So we can solve a whole variety of problems like this. And things are wonderful. There is one problem. And the problem is if we have repeated roots. So if I give you repeated roots, there are issues. So people okay with this board? Can I erase this? So the main reason I wanted to do this is how you handle repeated roots. It's a really nice trick. So for a lot of things this semester, what I care about is not the final answer, but the method used to get to the final answer. So how many of you who have seen recurrence relations have seen how to deal with repeated roots? Okay. Do you remember the solution and how you get it?
It just looks very similar to differential equations.
It looks very similar to differential equations. So difference equations, which is what we're looking at now, these are finite versions of differential equations where you move in discrete time steps. So let's say I give you now an plus 1 is equal to 2an minus an minus 1. So if we guess an is r to the n, we would get r to the n plus 1 minus 2r to the n plus r to the n minus 1 equals 0. So we'd get r to the n minus 1, r squared minus 2r plus 1 equals 0. This is going to give us r minus 1 squared equals 0. We should have two independent solutions because I have two free parameters, a0 and a1, or a1 and a2, or a17 and a35. Once I choose any two values of a, everything else is uniquely determined. There are 2 degrees of freedom, so I should have a 2-dimensional solution space. This is a 1-dimensional solution space. And so it turns out that there is a solution when you have repeated roots. And what you do is the following. So we're going to do perturbation theory. And the idea is you take something that works in the generic case and you try to see what happens as you push it to an extreme. So let's tweak the equation. So let's assume we now have an plus 1 equals maybe 2 plus epsilon 1 an minus 1 plus epsilon 2 an minus 1. And the idea is if I tweak these just a little bit, I should be able to force myself to have 2 distinct roots. And you might even be able to do that by only tweaking the first one over there. So maybe we can even keep this one to be 1. Okay? So let's imagine we perturb by, say, epsilon. And now we have distinct roots, R1 of epsilon and R2 of epsilon. Okay. Epsilon might be a pair of numbers. Maybe it's epsilon 1, epsilon 2. Maybe I'm just tweaking 1. But the idea is it's really hard to have a repeated root. You've got to have your characteristic equation having double zero. No, that's rare. So a small tweak should be enough. So we know the general solution. We would write it as C1 R1 epsilon to the n plus C2 R2 epsilon to the n. another way we can write this. We can write it as the following. We can write it as, I'll do it as gamma 1, R1 of epsilon to the n plus R2 of epsilon to the n over R1 epsilon I'll just do it like this first. Plus gamma 2 R1 to the epsilon to the n minus R2 epsilon to the n. And so I claim this is another way of writing the solutions. And if you look, I'll have gamma 1 plus gamma 2 R1 to the n, gamma 1 minus gamma 2 R2 to the n. I can solve for the gammas in terms of the c's or the c's in terms of the gammas. So the span of this is the same as the span of this. Okay? Well, I can change gamma 2 now, and if I wanted to, I could divide this by R1 epsilon minus R2 epsilon. And that would just change my value of gamma. I'll call it gamma tilde now. Because for a fixed value of epsilon, I'm just dividing it by a constant. The roots are distinct, so I'm not dividing by 0. And that will just change the value of gamma 2. So it's still going to be the same span. All right. Now, as epsilon goes to 0, what does this expression look like? So what will this look like as epsilon goes to 0? Study the limit as epsilon goes to 0 of R1 to the epsilon to the n minus R2 epsilon to the n over R1 to the epsilon minus R2 to the epsilon. Does this look like anything to you? I'm sorry? Well, the numerator looks like 0, and what does the denominator look like?
0.
We've got 0 over 0. Where have you seen 0 over 0 before? L'Hopital. L'Hopital's rule. We've got 0 over 0. So then the question becomes, how should we view this? This is essentially a derivative. And so I want to basically say this is essentially the same as the derivative of f of epsilon is r epsilon to the n, something like that. So there's a lot of ways you can try to write this. I could write it as maybe, R1 to the epsilon is going to be that limit plus, some error term, and then some function here, g of epsilon. There's lots of games you can play. The question is just, how rigorous do we want to do this? What would be nice is if we had maybe choose things so that R1 of epsilon is equal R, and, well, let's maybe do it this way. R2 of epsilon is equal to R, and R1 of epsilon is R plus epsilon. You can't necessarily do this, but let me just do this to make the algebra a little bit nicer now and illustrate what's going on. Imagine I choose my epsilons in such a way so that the first root is R plus epsilon and the second root is R. Then I would have the limit as epsilon goes to 0 of r plus epsilon to the n minus r to the n over epsilon. This is the definition of the function r to the n. And you would get n r to the n minus 1. Or if you wanted to do L'Hopital, you could do L'Hopital, but you have to remember that you're taking the derivative with respect to epsilon. Epsilon is your variable now. So this is suggesting that the second root should be like n r to the n minus 1. since r is fixed, I could write this as 1 over r times n r to the n. And what this is telling you is if you have a repeated root, you don't just have r to the n and r to the n, you have r to the n and n r to the n. If you had a triple root, you would have r to the n r to the n, and what else? N squared r to the n. If you had a quadruple root, you would have an n cubed. You go up to one less. So the idea here is I just want to give you some sense of how you can attack a variety of recurrence relation problems. This is the method of divine inspiration. If you have a solution, can you use it to somehow migrate to another solution? And the idea is we had two solutions, R1 and R2, and by looking at the right combination, we have something that has a nice limiting value. And so if we just did it this way, well, as epsilon goes to 0, they both collapse to the same thing. But if we do it this way, and we divide this by R1 minus R2, then this solution is going to go to something different. So that's a much better way of combining things. All right. There is a lot more that we can do on recurrence relations, and we probably will do a lot more on recurrence relations. This is just to get a few things out there. What I want to do for the rest of the class is talk a little bit about the most important inequality in all of mathematics and some of its consequences. All right. Anybody have any thoughts as to what is the most important inequality in all of mathematics? Anybody know any inequalities?
0 is less than 1.
0 is less than 1. More generally, if x is a real number, then x squared is greater than or equal to 0. This is probably the most important inequality in all of mathematics. It's amazing how many things come from that. So what we're going to look at now is what's called the arithmetic mean geometric mean. Arithmetic mean, geometric mean. Everyone here has looked at the arithmetic mean before. So I give you some numbers, a1, a2, all the way up to an. And we'll assume they're all greater than 0. If there are negative numbers or if some of them are 0, it becomes trivial. The arithmetic mean is the sum divided by n. So this is the arithmetic mean. The geometric mean is their product, and then you take the nth root. And one side is always greater than or equal to the other side. So what you may be noticing is, unlike a lot of other classes, I'm not asking you to prepare for class. I'm not asking you to do much reading. This is deliberate. I want you to be thinking on the spot. I want you to get practice thinking on the spot. I'm not telling you which side is greater than or equal to. I'm just telling you that it always works one way. How would you try to figure out which side is greater?
Try a bunch until you find two that are different.
Try a bunch. So what's a good one to try? If you choose the right thing, it's really trivial. Yeah, put one of the a's to be 0. You know, I told you that's supposed to be greater than 0. We'll take the limit as one of the a's goes to 0. As one of the a's goes to 0, what happens to this? Goes to 0, right? So you know it's got to go that way if it goes any way at all. This is what I want you to get to the point where you can do, where you can look at these things and figure out what test should I sniff and look at quickly. You could also try the case where they're all equal. And if they're all equal, it turns out that both sides will be the same. You have a lot of symmetry here. If I put a in meters, this is going to be meters to the n to the 1 over n. This will be in units of meters. And this will also be in units of meters. I can actually rescale things. I can assume if I want that the product of the a's is 1, or I could rescale if I want and assume that the sum of the a's is 1. So whenever you have abilities like this to rescale, to do it without loss of generality, it sometimes makes the problem easier. Given a bunch of numbers whose product is 1, show that their average is at least 1. That's essentially what the arithmetic mean is saying. So we want to prove this. What do you think we should do to start building up intuition on why this might be true? What should our step 1 be? So I'm giving you this, I'm claiming this holds for all n. What should you do to try to build intuition? Okay, which case? There's one case that you can say, and I will say that's too easy. Yeah, if you try n equals 1, so a1 divided by 1 compared to a1 to the 1 over 1. Okay, n equals 1 is trivial. But if we try n equals 2, now we've got a1 plus a2 over 2 versus the square root of a1, a2. What should we do to both sides? Square. And in fact, I might even put the 2 over here just to make it a little bit easier. Right? So if I square, I get a1 squared plus 2 a1, a2 plus a2 squared versus 4 a1, a2. I bring this over, I get a1 squared minus 2 a1, a2 plus a2 squared versus 0. Now I notice this is just a1 minus a2 squared versus 0, and now we use the greatest inequality in mathematics. We know that the square of any real number is at least 0. So now we know it has to be greater than or equal to, and that just propagates upward. So this proves the arithmetic mean, geometric mean in the case when n equals 2. That the average of two numbers is at least as large as their geometric mean. The question is, do you feel satisfied? Do you feel like you understand why this is true? Or is it just algebra happened? To me, this feels more like algebra happened. So the question is, can we give a more geometric proof? So we've got about 5 minutes left. So there should be enough time to give a geometric proof. And then the question, of course, is, how do we prove this in general? So you can prove this by induction. One of my favorites is a backwards induction, where you prove it if n is a power of 2, and then collapse downward, so that if you know it for some value of n, you know it for younger values of n. Some really, really nice tricks you can do. All right, so let's do the geometric proof. How many of you remember your geometry? Circles and lines and all those beautiful theorems? I always did the geometry part of the math competitions in high school because it forced me to keep geometry fresh. It has now been well over 20 years. Most of it's gone. But so with a reasonable assumption, this is a circle. And I'm going to choose, here's my A1, here's my A2. So the diameter is A1 plus A2. So what's the radius? And geometrically, what is the radius? In terms of what we're trying to prove, this is the, it's the,
Geometric mean?
no! Arithmetic mean. It's the sum of the two numbers divided by 2. This is the arithmetic mean. Right? So the radius of this circle is the geometric mean. It's now you got me doing it. The radius of the circle is the arithmetic mean. I am very programmable. But now we know physically, when we have a circle like this, the radius of this, okay. Now, what kind of triangles do you like? Equilateral triangles. What else do you like? Right triangles. So if you had to choose, it's going to be hard to get an equilateral triangle into this, but right triangles, where would you, so all of geometry, any really good proof requires you to draw an auxiliary line somewhere. Where do you think you want to draw that line? Okay, where do we want to draw the line?
The radius.
So One possibility is to go straight up there. There's another place where we could draw it. Where else could we draw it? Well, no, we could draw it up, down at the radius. That's a fine point. But there's another natural point in this problem.
They split.
Where they split. You know, basically, where is shit happening? Okay? When you look at this, where's the action? Center and that point. Those are the only 2 points where things are maybe going on. Possibly the extremes. But when you think about it, where is things happening? It's happening here and here. This is a good place. Okay, also I guess things are happening there. So these are the natural places. Now this gives me right triangles here and here. Can you think of any other right triangles we can get? We might have to draw some more lines.
I guess at that point if you wanted.
So where should I draw, which things should I connect? So if I call these points maybe A, B, C, D, E, and I'll call that O for the center. What other point should I connect?
E to the center.
E to the center. All right, that's a possibility. Where else can I connect? E to C. A to D, and A to E. And in fact, that's going to be a right angle up there as well. So it turns out, I don't think we actually need the E to O, O to D. But we have a right triangle here, and then by symmetry, if this is x over here. So this whole thing is a plus x. So we can start playing some games. We could call this maybe y, we call this z, and we can start looking at all the different right triangles we have. So we would have a1 squared plus x squared is y squared. And then we would have a2 squared plus x squared is z squared. And then we would have y squared plus z squared is a1 plus a2 squared. And now if I add everything up, y squared plus z squared will cancel with the y squared plus z squared. The a1 squared plus a2 squared will cancel with the a1 squared plus a2 squared here. And if I add everything up, when the dust settles, I'll get 2x squared is 2a1, a2. So x squared is a1, a2. So x is the square root of a1, a2. That's the geometric mean of a1, a2. So by using the Pythagorean formula many times, we get that x is the geometric mean. I take it back, we do want to have EO. This is the geometric mean. I'm sorry, yes, this is the geometric mean. And this is the arithmetic mean. They are on a triangle together. What kind of triangle are they on? A right triangle. And the geometric mean is a base, and the arithmetic mean is the hypotenuse. Hypotenuse is greater than the base. There you go. And that's a geometric proof that the arithmetic mean beats the geometric mean. All right, so I will send you some stuff to be thinking about for the weekend.